Welcome to Geology Talk, our monthly gathering of geology enthusiasts. And we have a great conversation today. We have Andrew Dunning bringing us the geology news. And then our special guest, Emma Mariko Rahalski, will be talking about her recent research trip to the West Pacific. Geology Talk is a production of the Geological Society of the Oregon Country. We're the oldest collaboration of amateurs and professional geologists in the Pacific Northwest, and a production of everyone else in the room who over the past 2 years have brought us such rich content. Because yes, this is our second birthday. We started this back in May 2020, kind of as an experiment to see what the community would feel like compared to our regular meetups and kind of what the format would allow. And it's been really gratifying to discover that not only have we kind of found that, using a 20-25 minute format that we have a little more flexibility in what we can offer compared to the sort of academic style lecture, but also that we're getting folks from all over the country to join us and all over the state. We've got our friends from the Geological Society of Minnesota and our friends in Bend and Prineville, Pennsylvania, Montana, California, Arizona. I'm probably leaving some of you out, but all of that contributes because there's a geological story wherever you are. And one of the things I love about this group is it allows us to kind of bridge the gap between amateurs and professionals and have the jargon explained. And for some of us who are kind of novice or amateurs to kind of learn from folks who have been in the field for a while, literally in the field. We also really appreciate the support we've gotten from the Portland State Department of Geology, which has provided a home for the Geological Society for the past 50 years, and financial support from the Beverly Vogt Grad Student Scholarship Fund. I think that's it for the announcements. So Andrew, when we last saw you, you were still working on getting some better sample dates for your field samples. So how is that going?
Well, I still am. I've received permission to dig a test pit, which is smaller than a trench on the fault scarp, which will allow me to get real, much better sort of context for individual pieces of charcoal in the fault zone. So I'm holding off on sending in anything until after I dig that hole. So that gives me the time to really refine the model for the age of the last earthquake. And I'll get much better and more reliable data from that time once I'm able to dig my hole at some point this summer.
Okay, so it's a bigger, as I recall, the problem was that stuff from the top, which is younger, was falling in and mixing with the stuff that was supposedly older, and that was kind of contaminating.
I was basically using a hand auger, and you really only get 10 centimeters of resolution with that, and it's polluted by stuff falling in from the top of your little core. So it's not the best way to do stuff, but you do what you got to do. But now I have permission to dig a larger hole, which will allow me to get really good precision in selecting samples, which is exciting.
Okay, well, we're looking for, I hope that goes well, and looking forward to the results.
Me too.
Tell us what's happening with the geology news.
All right, we got some cool stuff going on. All right, so this is the geology news for May of 2022. And I'm going to start out, like I always do, with global earthquake activity, being an earthquake scientist. The biggest event in the last month was a magnitude 7.2 right here in Peru. That's obviously quite a large earthquake. We've only had one of this size in the United States since 1993, and that was the Ridgecrest event in 2019. But this is a very major earthquake and obviously has a high capacity for damage. But interestingly, it was what's called a deep focus earthquake. It was centered remarkably deep into the Earth's interior, 218 kilometers down. Normally, earthquakes are detected, in the 10 to 20 kilometer range of this size. So this is an order of magnitude deeper into the Earth, and these deep focus earthquakes are really interesting and somewhat enigmatic. But it was centered in a sparsely populated area, and as a result, there are no reports of any damage or casualties as a result of this event. There was a similar magnitude 6.8 in northwest Argentina down here. Again, limited minor damage, but it's a sparsely populated area, so that makes sense. And there was also a magnitude 4.7 in Hawaii, which is related to the subsidence of the volcanic massifs, which are heavy and they weigh down and bend the oceanic crust. And you get earthquakes as a result of that. And all of these events, I wasn't able to find any reports of major damage or anything. This is the most earthquake-prone region in the world, where there are, I don't know, a half a dozen different subduction zones that cause both major massive earthquakes and smaller, moderately sized ones like these that are popping off all the time. Here is all of the earthquakes in the United States for the last 30 days. This is really standard background seismicity. We see some large clusters here in Oklahoma and West Texas, which are related to hydraulic fracturing in the gas fields out there. And we have the traditional intermontane west, sort of Wasatch Lane, whatever this one's called, I can't remember, here in the deflection, and of course in Southern California. This is all normal background seismicity. Largest event in the US this month was a 4.3 near Trona, California, located right here. Whoops. And that's an aftershock of the 2019 Ridgecrest earthquake. In Oregon, we had one sort of, moderately feelable earthquake at 2.7 in Molalla, and you might have felt that if you were standing directly on top of it or laying down at the time. And it was a reverse fault earthquake, which is caused by convergence. The subduction zone off our coast is squeezing Western Oregon, and this occurred really at the base of the crust, 24.7 kilometers down below the surface. So it's all normal processes. And we are glad that these little ones are happening. Moving on to volcanic activity. There are currently 25 ongoing or new active volcanic eruptions. There has been substantial activity this month at Fuego in Nicaragua, Nevado del Ruiz in Colombia, and Sakurajima in Japan, southern Japan. It's one of the most active volcanoes in Japan, so that's going off all the time as well, with minor ash eruptions and occasionally larger ones. So on to some research that's been going on. So in January, we had the massive volcanic eruption on the Hunga Ha'apai volcanic edifice, which is part of the Kingdom of Tonga. And we have the first sonar imaging of the volcano after that eruption. And if you recall, that eruption was the largest one seen since the eruption of Pinatubo in 1991. So that was a major event that sent shockwaves and tsunami all across the world. So before the eruption, this central crater was about 150 meters deep, but now it is over 4 kilometers across and 850 meters deep. That's over 2,800 feet. So this is a huge hole. And all of this material presumably was ejected during the eruption. And that allows us to estimate the amount of material erupted, which is about 6.5 cubic kilometers of material. And just for comparison, Mount St. Helens in 1980 spat out 1.3 cubic kilometers. So this is roughly, this is 5 times as much stuff got spat out during this eruption. And just for fun, I added this differential map, differential sonar map, and this is an analysis of the seafloor around the volcano that shows that the general topography is about the same, but the colors here, the red and the blue, reflect either a raising of the seafloor in elevation or a lowering in the seafloor's elevation. And here on the volcanic edifice itself, we see that it sank down about 40 meters, which makes sense because as all of the magma erupted from the volcano, it sank down. And all around it, it has gained as much as 40 meters in some places. And this is because during the eruption, there was ash and material raining down around the volcano and pyroclastic flows that were spreading out in all directions. And this deposited huge amounts of sediment on the ocean floor. And interestingly, some of these created ripples that were visible in the sonar that extended for some 50 kilometers in all directions. Which is very cool, very impressive volcanic eruption this was. This is one that I found particularly interesting coming from the UK. Some researchers have been looking for the sources of some of the largest stones used in Stonehenge. Now, we've known the source of the blue stones, which are the smallest stones around the inside of Stonehenge itself. These blue ones on this little figure here. And they come from Wales, mostly all over the place. There are a wide variety of lithologies. But these largest stones, the ones you see, the big ones that are laying on top of each other, that you think of when you think of Stonehenge, those are megalithic stones called sarsens, and they weigh roughly 20 tons apiece. And no one had really figured out exactly where they came from before. There had been a lot of ideas going back to the 1700s that they may have come from an area called the Marlborough Downs or the Chilterns, which are hilly areas in the Salisbury, sort of southwestern England region. But some researchers recently did some geochemical work on some stolen rock cores that were drilled in 1958. So Stonehenge has been restored quite a few times over the years, where rocks fall over and then they just put them back with a crane. And in order to do that and preserve the integrity of the rock, they drilled some holes in and put some bracing. And the rock cores that came out of these brace boreholes got stolen. And eventually one was recovered a few years ago, and they sent it out for whole rock geochemistry, and it matches with a site roughly 20 kilometers north of Stonehenge, here on Knapp Hill, part of the Marlborough Downs hilly area. And so these stones were taken roughly 20 kilometers from their source stone area down across the Salisbury Plain to where Stonehenge is today. So that's very cool, very interesting work. Now, over in Iceland, where we had that dramatic, effusive basaltic volcanic eruption in really all throughout last year, which occurred in this area, this part of Iceland on the Reykjanes Peninsula in the southwestern corner of the island, we've been some satellite radar measurements using a process called INSAR, and that is interferometric synthetic aperture radar, which is kind of a mouthful of words. And that's when we use a satellite just goes over and maps the surface on each pass it goes over. And that allows us to, again, create a differential map, which measures how much the ground has changed in that time. So in this same area as this 2021 eruption, we have roughly 4 centimeters of magmatic intrusion really over the last several days. So significant material is accumulating underground, and maybe we'll see some more eruptions at that site in the near future. This one was particularly interesting for me. Some researchers have determined some really fantastic characteristics of the very base of the Hawaiian hotspot. So the Hawaiian hotspot starts at the boundary between the outer core and the base of the mantle and extends all the way up to where the Hawaiian Islands are now, which allows them to be volcanically active. And at the base of this plume, we've known for several years of a roughly 900 kilometer diameter ultra low velocity zone, where seismic waves traveling through the inside of the Earth substantially slow down in this area and get trapped and reflect around. And using a handful of earthquakes from the Western Pacific that were detected over here in North America, these seismic waves get refracted and bent by these ultra low velocity zones and just generally the variations in rock temperature and density throughout the mantle. And using some extremely complex computer analysis, they're able to determine the kilometer scale resolution of the base of the Hawaiian hotspot plume, that's incredible. This is an area that is roughly 2,200 kilometers down into the surface, which is just mind-boggling. And they determined that this area here at the base of the plume, which slows seismic waves by 40%, is probably accumulated iron melt coming out of the Hawaiian hotspot plume. So material, melt and heat and liquid rock is coming up out of the core mantle boundary here, feeding the hotspot plume. But the iron-rich melt of the core is too heavy to continue to be brought up in the plume, so it settles out into this pool, likely of iron-rich melt at the base of the hotspot plume, which is crazy, mind-boggling, highly complex mantle physics going on here. Really impressive work by these researchers.
Andrew, some is going up and some is coming down.
Yeah.
So there's a kind of convective area, like a cloud forming or something from that boundary. Is that how do you understand that? I'm boggled as well.
So this material is going up. It's rising because it's hot, and as it rises, it melts. But the iron-rich melt that is already present at the edge of the core, it's already liquid, and as it rises, the pressure decreases, and some density-related things happen, and it just sort of settles out in an area where it's above the core but below the hot spot. The physics all behind that is beyond me. I'm an earthquake guy.
Okay, that's fascinating, and maybe Emma will have something more to tell us about hotspots. And I didn't realize that we understood the hotspot down to the level of the core to that extent. And you said it was a 1 kilometer resolution.
Yeah.
At a depth of, what was the depth again?
2,200 kilometers.
2,200 kilometers. That is amazing.
Or even more than that. On this figure, their cross section shows down to, it looks like 2,700 kilometers. So yeah, just incredible analysis that was being done here.
And that's part of the way that we get that kind of resolution is the sort of tomographic, having multiple seismic readings from all over the planet, and we kind of put together an image of what's going on down there.
Yeah, they selected earthquakes that were more or less antipodal on the opposite side of the world, or as much as you, from the opposite side of the world, if you draw a straight line from the continental US to the Southwest Pacific. So the earthquake happens over here, and it is refracted by this ultra-low velocity zone. And that is this track down here, which is the most refracted, most bent seismic waves. And they used several hundred seismic stations across North America to figure out highly precise seismic wave velocities. Some of them actually got trapped in the low velocity zone and were reflected back and forth a whole bunch of times, which is, that's amazing.
That is amazing. Okay, thank you.
Yeah, and on the same topic as seismic waves, we've got the largest Mars quake ever reported. So NASA's InSight lander deposited the first seismometer on the surface of Mars. Well, the second one, but the first one that actually worked. And it recorded the largest Mars quake ever, roughly a magnitude 5, about a third of the way around the planet from where this Mars InSight lander is located. And we think this is about the upper limit of the size of earthquakes Mars can generate, just based on the temperature of the crust and the composition of the crust and the size of the planet. We're able to sort of guess about that being the upper limit during the time scale of this InSight mission. And unfortunately, it is nearing the end of its days. The solar panels on the lander are completely covered in dust, and it will probably be phased out as the year goes on. But in that time, we've gotten some great data on earthquakes on Mars. Now, this is another one that sort of tickled my fancy. Deep in central Australia, there's an area called the Officer Basin, which is a very thick sedimentary sequence, including areas of rock salt or halite, and fluid inclusions in some of these rock salt crystals contained microorganisms from 830 million years ago. This is called the Brown Formation of Central Australia. And it, here in the stratigraphic column, we can see how thick it is. It's roughly 1.5 kilometers thick. And the rock salt formations come from the very base of it down here. And ultraviolet photography of these rock crystals, see, this is 20 micrometers. So this whole field of view is about, what is that, about a millimeter? I think so. Either way, the ultraviolet photography of these salt crystals shows small fluorescent blobs. Each of these little blobs, each of these little blobs are consistent in size and shape of prokaryotes and eukaryotes, some very basic, simple microorganic life forms. And these salt crystals have demonstrated that evidence of life can be preserved over immense timescales. We're talking 800 million years in certain environments. And these researchers were particularly excited about that because it has implications for the search for extraterrestrial life forms. If we're cruising around on Mars and we hit a bed of halite, for example, we can try and looking really up close to some of these crystals, and maybe we can find evidence of microorganisms on different planets. So that's very cool, very interesting preservation of material. And that is all I have for you this month. I'll see you in June.
All right, we're looking forward to that. We have a couple questions from the chat. How does the ultra low velocity zone develop? And what about the material causes it, if we know, or if you're willing to speculate?
The rock here is so hot, seismic waves travel much slower through liquid. And so this area here is so liquid that it's just super, super hard to transmit seismic waves through it.
So it's a measure of heat. Whenever the velocity is inversely related to heat. Am I getting that right?
Yes.
Okay.
More or less.
More or less. Does it tell anything? Does it tell us anything else about the composition, or are those inferences that you make based on other
basic sort of physics and geochemistry tell us what kinds of minerals and what they're made of are likely to exist at depth. And besides, we've actually even gotten chunks of this sort of material that show up in trace element analyses of Hawaiian lava. So we have a good idea of what's down here.
Okay.
Which gives us a really good idea of the total composition. But yeah, this ultra low velocity area is mostly liquid, which is why it shows up as such a low velocity zone, because it's surrounded by the more solid lower mantle rock, which is why this sticks out so well.
Okay, it's just fascinating that we're learning something that is, it's just fascinating to me. And we have another question. Why is the Australia's Officer Basin named the Officer Basin? Are officers buried there?
I have no idea.
Someone else can Google that and put it in the chat.
My best guess is that it's named after somebody.
Yeah, I think that's a good guess. Maybe someone named Officer or someone named Basin. I don't know. Do we know the mechanisms for Mars quakes, since Mars does not have plate tectonics?
Mars does not have active plate tectonics. Mars has had tectonic processes, but not necessarily in plate form. So, figuring out why these Mars quakes are happening is part of the reason we're studying them. I know there's been some good, both actual and sort of theoretical research into that field. I'm not well versed in it at all. Some of them are probably due to just subsidence and, the weight of Mars's volcanoes. I'm not really even sure if we have enough. I don't think we have enough seismometers on Mars to figure out what kind of earthquakes they are in terms of how the rock is fracturing to generate these earthquakes, whether it's moving past each other, moving up or down, or being stretched or squished. So this is something we will only learn more about with time. It's really hard to say, especially for me. I don't know. It's hard for me to say right now.
So instead of hundreds of seismographs on Mars, as we have on Earth, we have 5, 6 on Mars.
I believe there's 2.
2, okay, only 2. All right. I think it's time for us to try to find another planetary geologist to come, and I think we need a lecture on some of the updates from the rovers and landers.
Yes, I agree.
Yeah, that would be great to have. Someone asks, is where do you get your geology news? Where do you find it? And sort of what are the channels that you have that keep you up to date on things?
So some of these came from Twitter. I follow a lot of researchers and they're always happy to share what they're doing. Patty Hyatt, who's in the chat today, always sends me the geology news bulletins that are put together by an enthusiast online, and I always use those.
Oh.
And sometimes I just see things coming across various other feeds. There's a lot of good stuff going on, and I can never, I just always pick my favorites. I can never squeeze everything I find into one of these.
That's great. I mean, it better to have your favorites and the things that people are excited about. So thank you again for a wonderful segment there. And I think we're about ready to go to Emma. If you have any more questions for Andrew and want to hang around after 1 o'clock when we turn off the recording, please feel free to do so. Emma, if you're feeling ready.
Okay, so first I want to thank GSOC for holding this meeting. I think this is a great idea. My name is Emma Rahalski. I'm finishing up my 3rd year at Portland State University, getting my Bachelor's of Science in Geology. And despite the topic of my presentation today, I'm actually predominantly interested in researching groundwater interactions with karst. But I had a wonderful opportunity to go on this research trip, and because of a connection that I made in part on a GSOC AWG field trip last summer to Central Oregon, where I met in person Dr. Emily Cahoon, who is pictured here. And after the field trip, a few months later, she reached out to me and asked if I wanted to go on this research trip out to the ocean that had been rescheduled because of the pandemic. And she encouraged me to apply, and I applied, got accepted, and a month and a half later, I was on a boat in the middle of the ocean. So here is a picture of Emily, and this is all of the female scientists that were on our research cruise. We took this on National Women in STEM Day, and here is an image of the research vessel. So the research expedition was called the KM 2201 Seagoing Expedition to the West Pacific Seamount Province. KM stands for Kilo Moana, which is the name of our research vessel. So the Kilo Moana is an oceanographic research vessel owned by the US Navy and operated by the University of Hawaii Marine Science Center. And if you see here on the back of the boat here is this little frame. And that is the frame that we actually use to dredge the seamount. So you can see it in this picture here too, and this is the dredge bucket attached to it. So this was a collaborative effort between Oregon State University, UC Santa Barbara, and University of Hawaii. And I have here a picture of all the scientists that were on the team. Normally on a research cruise like this, you could have about upwards of 20 scientists working on a cruise like this, but because of pandemic rescheduling, pandemic restrictions, and various complications, we had a really small crew this year. So we had 12 scientists, and because of that, everybody had to work really hard to accomplish the same amount of work. We set out to do, I think our initial goal was 32 judges, and we ended up doing upwards of 40 judges. So we were able to accomplish a lot. So yeah, and we have here Tiana Casey, who's also a GSOC member. She goes to Northwest Indian College, but both me and Tiana were there as representatives of Oregon State University. So what were the research purposes? We set out to dredge ocean seamount basalts from the Rurutu and Samoa hotspot chains. We were also hoping to map the seamounts that we passed over and map the ocean floor that we passed over along our trip. The basalts that we dredged are currently en route and transport to their respective universities, where they will have geochemical and geochronological analysis performed on them. From the data from those analyses, we will be able to construct a plate motion model for the time period of 80 to 100 million years ago. And we'll also be able to observe long-term compositional variability of hotspots and their sources. Another really cool implication is potentially being able to observe the connection between a large igneous province and a seamount chain. So the large igneous province is the Ontong Java, and the seamount chain that we're looking at is the Louisville hotspot. So the research area, just to give a little bit of an idea of where we were, because I know before I went on this trip, I had no idea where the West Pacific seamounts were. So this is Hawaii in the Emperor Seamount Chain, just for reference, because most people know where that is, in the Louisville Seamount Chain. And I do want to highlight that this bend here in the chain, this is different than the bend that I will be talking about in the next slide. There were two main bends in the Pacific Plate that we know about. So there was the one that happened here, that's about 50 million years ago. And then there was an older bend, which we think happened around 88 million years ago. And that bend does not show up on the Hawaii and Louisville seamounts anymore. It's either been obscured or subducted. And this is the Ontong Java Plateau. And here's our research area. So this is a map that shows the zoomed in image of the research area. So essentially we boarded the Kila Moana in Hawaii. We sailed across the Pacific, came in, judged these upper seamounts here, and then came down and judged these lower seamounts, and then crossed the trench and port in Guam. So why were we looking at the West Pacific seamounts? These seamounts reflect the oldest oceanic hotspot seamounts in the world. They're between 80 to 100 million years old. Current plate motion models for this time period are based off of estimations from much younger ages obtained from Hawaii and Louisville hotspot chains, and are not based on geochemical data such as we will be collecting on this trip. So our goal is to use the isotopes and trace elements in these seamount basalts to connect each seamount to a mantle source and create a timeline for their movement. And from that, we'll be able to make the deepest time oceanic plate motion model, which is pretty exciting. Another very interesting implication is potentially connecting the Louisville hotspot chain to the Ontong Java Plateau. So if you noticed, our research area is not where Louisville hotspot or Ontong Java is. So I'll explain a little bit how we're able to connect those given where we're going for our research. So here is an image from two images from the project proposal. And up here, this is our research area. And we have Louisville hotspot here. The darker paths on each of these is the older model, the current model for plate motion, and where it places that 88 million year old bend. And these lighter paths are where we think the current bend is. And the reason why we think the bend is farther north than the current model, if you look at this, this zoomed in image of our research area, we have the darker path, and all of these little dots are seamounts. And if you see underneath there, we don't have any seamounts where the old model passes through. However, farther north, there's a lot of activity. So this is why we think that this bend is actually a little bit farther north than the current model. And if you look at the Louisville hotspot chain, the path for that, the current model, if we move it farther north, then it actually places Louisville beneath Ontong Java Plateau. And the reason that's very interesting is because there's a lot of ongoing research about the connection between the emergence of a mantle plume and hotspots to the existence of flood basalts. And it can be very often difficult to research this because flood basalts obscure everything in their path because of the massive volume of basalt that's erupted. So this research cruise gives us a really unique opportunity to look at what's happening beneath flood basalt without actually having to see the hotspot beneath the flood basalt itself. So I think that's really exciting. So how do we construct an absolute plate motion model? We need two main components. You need geochronology, which we use the potassium to argon decay chain, and that gives us the age of the seamount itself. And we use geochemical analysis, and that anchors the individual seamount to a mantle source. And the way that that works is that each hotspot is connected to, at the time of eruption, a mantle plume, which has a source that is deep in the mantle. And each mantle source has a unique geochemical signature. That signature is detected using different relative abundances of strontium, neodymium, hafnium, and lead. So if we can observe those relative abundances, we can connect these seamount to their mantle sources. This is a couple images that kind of explain how we do that. This image here is from a previous paper by Jasper Conter, who was one of our head scientists on the research vessel. And I like this one because it has the geochemical signatures of some familiar volcanic features. And as you see here, when you graph out the relative abundances of strontium, neodymium, hafnium, you can kind of make these areas of where they will plot based on their mantle source. And the second image here is the two hotspots that we were looking at, the Rurutu and the Samoa. And you can see how when you look at the neodymium and lead isotopes, they plot in very distinct areas. And so that's the general concept behind that.
Emma, can I interrupt for a second? So
Sure.
there's a seamount, and you get a signature from the seamount, and then there's a larger area. Is that the igneous province where there's a larger area where the volcano has the flow has gone? I'm trying to understand that.
So I'll go into that a little bit. So we don't necessarily know the hotspot chain. So you have a mantle plume which connects to a hotspot. So the mantle plume is a chunk of the mantle that is upwelling, and then it intersects with the surface. And then the plate above it is moving, and the mantle source is relatively stable. And as the plate moves, you get eruptions that occur along that plate from that stable source. The large igneous province is a separate entity, which we don't actually know a lot about, but they're large, vast extents of massive volumes of basaltic eruptions. But we do often see them kind of spatially near each other, such as with the Columbia River basalts and with the Yellowstone hotspots in the Snake River Plain.
So is the assumption that the mantle plume has consistent geochemistry, and that gives you the signature over the course of the hotspot track?
Yeah, I'm not sure if it's consistent as much as distinctive. I think one thing that we're looking at is how these signatures change as they get progressively older. But I do think that they are fairly distinctive. So even though, go to the previous slide, or wait, the next slide. Yes, so even though they might be changing within this area, I think that any distinctive source will be able to plot around in this area.
Fascinating, thank you.
Of course. So I have here a video of this LIBS machine that we had on board on the boat. So a LIBS machine, a LIBS analyzer that you would have in a lab could cost upwards of $20,000. However, our head scientist on the trip was able to build a LIBS machine, which is a laser-induced breakdown spectroscopy, which is a destructive analytical method. And he was able to build this using a tattoo removal machine. So here is a tattoo removal machine attached to this base here, sends this laser and breaks down a little square of the rock, which gets set into a mass spectrometer. And then that sends a geochemical profile into a computer. And I have a video here that just shows what that looks like. I don't think there's any sound on any of these, but yeah, so that's the laser. And there's a little chunk of a rock that's in there, and sorry. So it's shooting a laser at that rock, breaking it down, and then sending it through into this. This back here is the mass spectrometer, and this is the relative geochemical profile that we get. And what's very cool about this is that it takes a long time to get the samples that we collect on the cruise to their respective universities. The research vessel has to do other expeditions after ours and then travel back to Hawaii. They have to be unloaded at University of Hawaii and then shipped to their university. The ability to do these geochemical analysis beforehand allows us to select certain samples that we can take home to our universities on flight or ship back to us right from Guam, so that we can start doing science right away, which is a really great thing that we're able to do.
That's amazing. So the laser is vaporizing just enough of the sample that you can get. I mean, can you explain what just for people who are not familiar with the method, how the spectrogram tells you what's in it?
Yeah, so a mass spectrometer will essentially, it uses centrifugal force to separate individual components by their different masses, because things with different masses will rotate at different radii. So that's what the mass spectrometer does. And the laser essentially, yeah, it turns a small square. You can see when you look up at the rock, it breaks up a small square and melts that down into plasma and sends it into the mass spec.
Wow.
So yeah, it's super cool. I'd never seen anything like this. So. So the second component is the argon-argon geochronology. So the argon-argon geochronological method uses the potassium-argon decay chain. So potassium decays to calcium and argon at a half-life of 1.25 billion years. And because argon is volatile, when the material is erupted as magma, all of that argon, which is a noble gas, will escape the magma. Then after solidification, all the remaining argon in the rock is a result of the potassium decaying to argon. So we can measure those relative abundances and determine how much time has passed since that rock solidified. Argon-argon geochronology uses the same methodology as far as the parent to daughter ratios, but instead of looking at potassium 40 and argon 40, what we do is we turn potassium 39, which is in relative abundance, like similar proportions to potassium 40. So you have a certain amount of potassium 39, you can tell how much potassium 40 you have. And we turn that potassium 39 into argon 39. And then we look at the relative abundance of argon 39 and argon 40. So we can look at argon 39 and back calculate how much potassium 40 we had. And the argon 40 tells us how much daughter isotope we have. So the minerals that we use in argon geochronology are amphibole, biotite, plagioclase, alkali feldspar, and clinopyroxene. However, alkali feldspar is too felsic, so we didn't see those in our results. And if you'll notice, anybody who knows the mineralogy of these, amphibole, biotite, and plag have potassium in their crystal structure. However, clinopyroxene does not. So the reason that we can use clinopyroxene is because we have melt inclusions within the clinopyroxene that are potassium bearing and then undergo the same decay. And oftentimes you will have a rock sample that has very little usable plag, biotite, or amphibole, but is very abundant in clinopyroxene because basalts are very abundant. So we can use those melt inclusions to do analysis on samples that we wouldn't normally be able to. And that's a method being, yeah.
It's probably roughly similar to the minerals that we have here in the Pacific Northwest in our basalts. I'm not getting you into the difference in the composition, but I mean, those are the same. You don't have alkali feldspar, but you do have biotite and plagioclase.
Yeah. Yeah,
okay.
they're all basaltic, so they're definitely similar. And yeah, so the method of analyzing the clinopyroxene is actually a method that's being developed at Oregon State University. And it's really cool how they do that. So I wanted to give a brief overview of how that's done. So you essentially take the basalt and you crush and sieve it, and you separate the individual CPX crystals from the basalt. And then you acid leach any secondary minerals from the grains. And then you put that copper tray with CPX on it into a vacuum. You can clean the surfaces of the grains using CO2 laser, and then you incrementally heat the samples and extract the gas, which is then put into a vacuum. The gas is then exposed to a getter, which is a reactive material that removes any reactive gas. Because argon is a noble gas, it's non-reactive, so all the argon is remaining. And then we put that gas in the vacuum into a noble gas mass spectrometer, which then separates in the same method that the other mass spectrometer did, the different gases by their mass. And that will tell us the relative abundance of argon 40 and argon 39 because they have different masses. And that's how we can determine the ages of the basalts.
I'm going to ask Andrew later if this is something similar to what he's having done for his for his samples in the Strawberry Mountains. But
I would love to hear about that.
Yeah, talk about that after this. So cradle to grave, go ahead.
Yeah, so the cradle to grave process, this was what happened on the boat before we do any of the geochemistry. The first thing that we have to do is map and pick a dredge spot. So all of the ocean floor is mapped using satellite. However, to get a really accurate map, you need to combine satellite and sonar imaging. And about 90% of the ocean floor is unmapped using sonar. So it's really important on these research trips to do as much mapping as possible. So we would be mapping on our entire trip. However, when we passed over a seamount, we would drive around it and map the seamount as well. So the way that sonar works is that it sends a sound wave down, and that sound wave bounces off the base of the ocean and then comes back, and the sonar detects the speed and the time at which it takes to come back, and that will give us elevation for the seafloor. This is a map that is generated using that method that we made on our trip. And you can see this is the seamount. And once we've mapped the seamount, we are able to determine our dredge path based on the drift direction of the boat, because we want to go perpendicular to the drift direction. So we figure out the drift direction, and then we find a flank of the volcano that we can dredge. We look for something that's highly reflective, and that is kind of a flank that extends away from the center so that we can avoid any sediments, and we are getting mostly basalt. And this here is an XBT, which is an expendable bathymetric thermometer. We essentially it's like a little metal wire that we send down in, and it gives us a temperature profile of the ocean. So temperature versus depth. And we use that to calibrate the sonar, because sound waves travel at different speeds in different temperature water. And we do that about twice a week. And then once we have picked a dredge spot, we go to the dredge site and we drop the dredge. So I've got this video here of the dredge going out. It's attached to this large frame, and the frame essentially extends down over the edge of the boat, and it's attached to this long, very strong cable. And we basically just drop that down into the ocean, and we use this to increase the payout of the cable. And yeah, so the dredge itself is built with these weak links, which are built to essentially break under a certain amount of tension. And that is to save the cable, because we only have one cable and they're incredibly expensive. So if the cable breaks, we have to stop the expedition. But if we lose the dredge bucket, we have extras. So this one, the top weak link, is built to break at about 12,000 pounds of tension, and the smaller ones are built to break at about 6,000, 7,000 pounds of tension. Once we drop the dredge into the water, we put this pinger about 200 meters up above the dredge, and this pinger sends a ping downwards and upwards, and that essentially tells us the depth that the pinger is from the ocean floor, which will give us a relative angle that the cable is actually at compared to the ocean floor, which can help us figure out how we're navigating around, especially when we get stuck, because that does happen. So once we drop the dredge in, we put the pinger on, we go up into the computer lab and we watch the tension, and we record in a dredge log tension spikes. So this was kind of an average, background tension that would be happening. Sometimes you would get spikes up to 8,000 pounds. When we're stuck, sometimes it spikes up to 12,000 pounds, and we're just hoping that the dredge bucket didn't break. The weak link did break, then it would drop all the way down. But yeah, we only lost, I think, one dredge bucket on the trip, thankfully. So yeah, and this we use to increase or decrease the payout, which can help us manage the tension on the dredge. And we watched this. Each dredge was it was 4 to 8 hours. So it's a long time of dredging. It's a very slow process. And then once we finished dredging, we pulled the dredge bucket up. Sometimes we had no rocks, but sometimes we had a lot of rocks. You never really know what you're going to get because you're going in blind. But yeah, when we did get rocks, we would sort them out based on what we think is basalt and what we don't think is basalt. And then we bring it into our wet lab and we saw it using this rock saw. The rock saw is diamonds all around the edge of it because that's a very hard mineral, the hardest mineral. It can cut all rocks. So we slice the rocks into like bread loaf kind of size slices, and we cut little individual billets of rocks that we think are have good quality minerals that haven't had a ton of alterations, that we can use that for geochemistry. And then once we cut up all those slabs, we bring them into our rock lab where we dry the samples, we weigh them, we take pictures of them, we describe them, and we select samples that we want to subsample, essentially send to the universities and do our geochemical analysis on. I have an image here of some pillow basalts that we got, which have this thing called a palagonite rind, which is what happens when you weather glass. So that's that orange rind there. And yeah, so that was, once we finished the sample processing, we basically put all of those rocks into little bags, and then those bags go into more bags, and then those bags go in other bags, and then those bags go in a room full of bags. And everything is labeled very meticulously because that part was run by Emily. And if anybody knows Emily, she's very detailed. So all of those bags go in this room. And I just wanted to put this video in here because it shows how many rocks we processed on this 6-week trip. So this is the room full of bags at the end of the trip in Guam. And we had to hand carry all of these bags out and load these onto like large crates, which were then get unloaded in Hawaii and then shipped to respective universities. So yeah, these were all of the samples that we collected, which yeah, we did quite a lot in that short period. And yeah, anybody who's interested in learning more about that process or following up on what happens afterwards, feel free to follow us. We, the fellow scientists, started an Instagram account where we were posting along our trip, and we have some more videos, and we also have descriptions of all of the scientists on the trip. If you wanted to look into that, you can either look us up at this Instagram account, West Pacific Seamount Province, or scan this QR code here. So thank you all.
Emma, thank you. That's a wonderful presentation. A lot of questions I think we're going to have in the chat, and that may take us a little long. We'll stop the recording at 1 if people want to stick around and ask more questions. But one of the questions we saw was, how is this project funded, and how much does it cost?
Yeah, so the project is an NSF grant. So it's funded by the National Science Foundation. Which is it's a very long process to get funding. It's very competitive. And I think that the main reason that they were really able to get this particular trip funded was because of the implications that it has for the connection of the flood basalts and hotspot seamounts, because that is a very hot topic for research. And this costs a lot of money. I think Emily might know.
Oh, actually, I see Dr. Cahoon has answered the question. $70,000 a day. That's very valuable. So what are the implications? What are there larger policy implications, or just sort of scientific paradigm shift implications in terms of how the large igneous provinces are interpreted and the hotspot tracks and all that?
Yeah, I think it's more of a paradigm shift. I think that large igneous provinces are, they dramatically change the landscape, but we don't really have a lot of knowledge on how they form, why they form, and if they're connected to hotspots, why that is. So I think that being able to concretely connect a large igneous province to a hotspot chain further gives evidence for the connection between the two, which is, I think it can be really hard to look into that connection because of the reason that I discussed earlier, that they obscure everything in their paths when they erupt, the large igneous provinces. So,
for you, with your interest in karst topography, which we don't have, we were talking about in the pre-show, we don't have a lot of that in the Pacific Northwest.
Definitely.
So you're probably going to be looking elsewhere in the world. But are there research methods that you learned in this process that you're going to be applying to the rest of your work?
I think just kind of seeing the whole process from beginning to end, how much work goes into it, gives me a lot more respect for, all of the planning that goes ahead of these research trips. It makes me realize that it's very important to know what your goals are, have backup plans, and just that whole process. There's a lot that goes into it. And as far as the geochemistry, I think, I will be performing different geochemical analysis, but radiogenic isotopes do occur in carbonates, and they are very commonly used for paleoclimate. So, yeah. So
there'll be some overlap there. I'm seeing more questions in the chat than I can actually focus on and answer. One of them that I was curious about is you're just dredging up loose rocks from the that have fallen off the volcano. I don't know if I'm describing that right, or you're not taking cores from the seafloor, are you? Okay. Yeah,
so they are a part of the seamount themselves. Some of them might have weathered from farther up. We do get a lot of volcaniclastic, which is essentially chunks of volcanic rocks cemented by chalk. But we do also get large pieces from the actual flanks of the volcano, and they all have very thick crusts of manganese on them. But yeah, we just take the bucket and we use that tension and we just scrape. And I thought that would be really destructive to ecosystems, but from what I saw, we we were really good at the ability to analyze and look at the reflectivity of the surface. Was really a great method for determining what was basalt and what was, sediments and habitat. So
because everything is down there is either volcanic or it's organic, or you've got some carbonate, you've got some chalk and other things, but it's basically you can identify what is the volcanic basalt pretty easily by looking at those basic minerals, those basic mafic minerals that you discussed earlier.
yeah, and also when the seamounts were, above the surface of the ocean, you have coral reefs growing around the edges. So once that starts to erode, all of the sediment from those coral reefs and all that life stays concentrated towards the center of the volcanic feature. So
I
that's why
forgot
we were
that.
looking at the edges.
I see.
Yeah.
I forgot that these were seamounts. You said that. Now I get to be the one who asked the stupid questions, because I'd forgotten that seamounts have then descended, leaving sometimes a reef coral ring behind. And so, okay, they were once above ground and they're not undersea volcanoes.
Yeah, and I think Hawaii is a great example of that, because you can see Hawaii, you have the big island, and then the islands get progressively smaller. And behind that is the whole Emperor Seamount chain, which are seamounts below surface, but yeah, we're once above surface, just like the big island. So,
okay. Well, we're going to stop the recording here in a moment, but I want to thank, and I think, Emma, if you can stick around and answer some more questions. And I think there might be some more questions for Andrew as well. So again, thanks to everyone who contributed. We'll probably have the room open for another half hour if people want to ask questions. And thanks especially for Gary for being our technical director. And Gary, you can now turn off the recording.